My name is Yong Lin Kong. I'm currently an assistant professor in the mechanical engineering department. My research goal is to address unmet clinical needs with 3D printed electronics. And what I'll describe is processes that allows us to integrate functionalities such as sensing and actuations into an otherwise passive mechanical structure. The integrations of bioelectronics with the human body could have a significant impact in the field of diagnostic, drug delivery, and smart prosthetics. This idea is not new. It was something that is of interest since even when I was still a high school student in 2002. And over the past decades, the advancement of bioelectronics has demonstrated the potential to diagnose, treat, and prevent diseases, partially restore and even augment some of the complex functionalities of the human body, and finally provide previously unavailable data that could help us to unravel the complex mechanisms of our body and our interactions with various diseases. Yet, such integrations is inherently challenging due to the geometrical, mechanical, and material dichotomies between conventionally manufactured electronics and our human body. A conventionally manufactured electronics, such as our smartphone, is an inherently two-dimensional planar rigid construct that is built with a top-down processes that often involve harsh chemicals and temperature processing conditions. And often to build a device, it involves assembly of modular components before it can be made into a complete device. In contrast, our body, such as ourselves and a husky, is a naturally grown biological system that is a three-dimensional construct that is grown from the bottom up under finely tuned physiological conditions. For an engineer like me, I really find biology to be fascinating. It demonstrates the exceptional capability to achieve control of local properties that we have so far not been able to achieve. For example, if we look at the bone structures, we can see a hierarchical, multi-scale structures that not only can adapt to changing environment, but is also highly optimized for a particular function. In contrast, engineered device such as our expensive smartphone is relatively primitive. It has limited control of properties and function, and is unable to adapt and heal, unlike a biological system. So when we are trying to put this together, it becomes very challenging, right? Because we are inherently a unique organism. How do we make electronics that in a unique unit of one in a cost-effective approach, which is particularly challenging considering that electronics first has to be made in clean room, with expensive tools and complex facilities, and current strategies to integrate electronics into a three-dimensional construct involve designing this beautiful and sophisticated architectures, right, that is then carefully and meticulously assembled into a three-dimensional construct. Now, as you can imagine, this is an extremely expensive process, especially since electronic manufacturing has been evolved for mass productions. So it requires the reproductions of identical device to reach the economy of scale. So as soon as we introduce, say, any degree of complexity or customizations, the cost becomes extremely expensive. Now, the other part you could also imagine, right, is also very challenging to build. This is speaking from my experience. I spent 2 years in clean room during the first 3 years of my graduate school. To me, it has been a traumatizing experience. I almost earned another Ph.D., permanent head damage. And so through this pain and struggling, really what we started to really trying to think differently is how do we build devices with a processes that is inherently compatible with the idea of making devices that is highly unique, that can be locally designed so that we can rapidly tailor those to a specific unmet clinical needs, and ideally can be remotely fabricated so we can build electronics, say, in the hospital or in the future space mission. So my research tried to, for example, leverage additive manufacturing processes, but here, in this case, is a type of 3D printing that allows us to integrate functionalities by incorporating, for example, nanomaterials. And using those processes, we can now build electronics directly on a three-dimensional construct. We can also build it with a desktop-sized platform without requiring any large equipment and complex facility. And finally, because this type of process is the cost per part is relatively agnostic to the increase of degree of complexity and degree of customizations, we are now able to build devices at a much lower cost compared to if we rely on conventional manufacturing processes. So my research really look into, for example, how do we control the depositions of nanoscale material in a predominantly micron-scale printing process using, for example, soft matter physics and evaporative-driven assembly processes. But importantly, we also look into, once we can patent those devices, how do we selectively post-process and heat and program mechanical and electronic properties during the printing process to create electronics? And finally, how do we leverage this toolbox, right, to build new type of electronic devices, such as ingestible gastric resident electronics that would otherwise be challenging or impossible to build using conventional processes? So just some brief recap on what we do. For example, we can take a 3D scanner to scan a 3D topologies and design the electronics to conformally match the three-dimensional construct. And that extend the reach of 3D printing to include the printing of not just passive component, but also active electronic functionalities. And what we are hoping to do is to leverage this to build, for example, patient-specific smart prosthetics or smart regeneration scaffold, where the nanomaterials provide active functionalities, and we can incorporate biological materials to enhance the biocompatibility of the device to the human body. Now, one of the key challenges to do that, and why this has not been successful so far, is really the inability to selectively post-process and heat the material during the printing process without damaging the underlying temperature-sensitive biological material. So very recently, in this unpublished work, we have developed, after 4 years of effort, a way to focus electromagnetic wave so that we can heat the printed materials and program the microstructures and properties directly during the printing process, allowing us to start to build electronics in 3D, as you can see here, even on temperature-sensitive constructs, such as polyethylene, silicone, paper, and biological material. And this allows us to start to build electronic component in 3D, such as in this case, right, we can build electronics just like the highway in Houston in 3D, so that we can have a much more smaller form factors, but also a more complex functionalities in comparison to trying to integrate them using a two-dimensional construct. We can also incorporate, for example, nanomaterials such as graphene, so that we can functionalize those materials to detect various biomarkers and print them on biological constructs. As you can see in this example, right, this is wireless sensors that can measure humidity on a leaf. We can also print on bone structures, and this is electronics on the bone that can measure the strain that is being experienced by the bone. And what I'm really excited to explore potential collaboration is also thinking about incorporating this approach to integrate electronics on existing biomedical implants, such as total joint arthroplasty, where, as you know, right, is an important biomedical device for the treatment of osteoarthritis, but suffer from complex complications such as mechanical instability and infections. And obviously, intuitively, right, if we can incorporate electronics, we can use those data to improve the clinical outcome. We can also use those data to improve future design of those implants. And this is not a new idea, but something that has been explored more than a decade, but so far has not been really clinically adopted. Because as you can see, right, it requires significant modifications of the existing implants, which introduce a lot of clinical risks and also cost to the system. So what we hope is to use this process to allow us to directly print and integrate into, say, biomedical implants so that we can achieve sensing and actuation, potentially actuations in the future for drug delivery with a cost-effective approach. So right now, we are also using, let's say, machine learning and machine vision approach so that we can build a desktop-sized platform that is entirely closed loop. For example, here, we have a laser displacement sensors that can measure the topological change of the structures during the printing process, and the machine is able to adaptively print on a three-dimensional construct. So that's one direction we have been approaching, right? Thinking about how do we incorporate sensing functionalities using a 3D printing process. In the next few minutes, I just want to talk about the other potential applications we can explore, in this case, incorporating actuations using a 3D printing process to build devices that would otherwise be challenging or impossible to build using conventional process. So one application we have been exploring is to use 3D printers to create ingestible gastric resident electronics, which are electronics that can stay in the stomach for an extended period of time. And that allows us to have implants in the body without, for example, a surgical process, and that could potentially also reduce the risk of inflammatory immune responses, because stomach is few of the organ in the body that has been evolved to tolerate the introductions of foreign material, such as the wonderful lunch we just had, right, without eliciting inflammatory immune responses. So using this approach, right, one of my funding explore how do we build devices that can stay in large animal and hopefully in the future human, right, for weeks. And another projects look into, can we incorporate active drug delivery system so that we can use our smartphone to trigger drug delivery directly into the human body. And third, one of our current projects by NIH look into, can we build structures that can actuate to different dimensions and can apply mechanical pressure into, say, the stomach. And we can use this for example, to help patients with obesity by inducing the feeling of satiation. So in the last 1 minute, I just want to show some of the latest work we have been working on, right, on how do we create a multi-stable architectures that is also entirely soft, which is a very important clinical considerations, right? We don't want to introduce ulcer with this type of device, but to do that, we have to design a metamaterial structures that can incorporate energy barrier that can also be actuated magnetically, as you can see here. And importantly, right, we can actuate it using magnetic field from external of the body and use that for shape changes. And we can also, through, for example, collaboration, design drug delivery system, as you can see from the bottom video, for delivering fluids wirelessly using this approach. So what we also have been developing is to ensure that it's robust in, say, a broad range of temperature from -20 degrees Celsius to 100 degrees Celsius, and can also resist mechanical forces, which is something that we expect. Let's say if you have the device inside the stomach, right? So we design it so that it's very robust. In this case, as you can see, it can resist impact force more than 4 orders of magnitude greater than the force barrier we programmed. Now, this is developed by a graduate student, so he really pushed the torture test, and he also put it on fire and show that it can continue to function. And really, this is the time I told him, you are ready to graduate. Right? So in general, my lab developed new processes and manufacturing features, manufacturing processes that allows us to incorporate active functionalities such as sensing and actuations to build devices that would otherwise be challenging to build using conventional processes. With that, I just want to thank my funding agency, and finally thank all of you for your time. I really look forward for potential collaborations. Thank you so much for coming to my talk. Thank you. Thanks.